technical challenges that you run into. So I tried to put together a small presentation, limited scope, that allows the relatively inexperienced ham radio person an insight into what this whole antenna thing is. You know, it's easy to drag out your checkbook, buy a radio and buy an antenna, buy a microphone, and find yourself on the air. But the thing that always seems to be a challenge for folks is the antenna. You know, a very great portion of the performance of your ham radio station revolves around the performance of your antenna. And if you have some understanding of what makes it tick, it certainly helps and allows you to get that performance that you're looking for. So tonight, we're going to talk about 15 terms. I'm going to define the terms and what they mean, because these are the ones that you hear all the time, and for some of us, they don't make sense. And the other thing we're going to talk about are 3 numbers. And I'd like you to try and remember these 3 numbers. They're not too hard. The number 1, I think we can all handle that. The number 468, and we'll talk about why that's important. And the number 300 million. Okay? Let's see if I can get this thing to advance. So the first term we're talking about is wavelength. You know, electromagnetic waves. Let's see what I'm going to say. Electromagnetic waves. Can anybody tell me what kinds of things are electromagnetic waves?
Light.
Light is an electromagnetic wave, as is a radio signal, as is a microwave signal, as are certain ultraviolet light and infrared light. They're all electromagnetic waves. They're all exactly the same thing. So, knowing this allows you to kind of delve a little deeper into this topic of what radio and antennas are all about. Let's talk about electromagnetic waves, their velocity. How fast do these waves travel? And the answer is that first number I gave you, or the third number I gave you, 300 million meters per second. That's the speed of light, which around here we always like to use 186,000 miles an hour. That's pretty fast, right?
Second.
Yeah, per second. So low frequency and medium frequency and high frequency and VHF, UHF, microwave light, they're all the same thing. So let's take a little closer look at this wave. And this symbol up at the top up here is lambda. And lambda is the term or the symbol that's used to define wavelength. So from the top of this sine wave to the top of this sine wave is one wavelength. And so the question is, how long is a wave? If you have a frequency of 1 hertz, anyone want to venture a guess as to how long that 1 hertz wave is?
Yeah, it's 300 million.
It's 300 million meters long.
Right.
That's a very long wave. So let's use an example that's a little closer to home. Remember, the velocity is the 300 million meters per second. Let's say we're going to look at a 30 megahertz signal, which is 10 meter band, right? 30 megahertz signal, we take 300 million meters divided by 30 million hertz, so that's 300 divided by 30, or a 30 megahertz signal is 10 meters long. Do you know now why they call it the 10 meter band? That's one of those things that's always kind of interesting. How did they come up with this term meter band? How did that arise? Well, that's the actual example of it. In fact, when you're dealing with light, they measure light in angstrom units, which is a very small fraction of a meter. Let's talk about reflected energy. We know how long a wave is. We know how fast the wave goes. Let's see what goes on with reflected energy. And remember, light and radio waves are exactly the same thing. They're just different frequencies. So if you take a flashlight and you shine it on a mirror, 100% of that light, or darn close to it, comes right back to you. Okay? Now, if you were to look at that in terms of radio waves, and what's our measurement for issues with radio waves? SWR, right? We're always talking about SWR. SWR is talking about reflected energy. So if you take a flashlight, you shine it in a mirror, anybody want to venture a guess what the SWR of the mirror is?
1.
Light through the mirror.
1.
No.
Infinite.
It's incredibly bad because the light is not going where you're trying to get it to go. It's not doing any work to be reflected right back at you. Make sense?
Yes.
Let's take the same beam of light and let's focus it on a matte black object on the wall. All of the energy is absorbed by the matte black background. What would that SWR be?
1 to 1.
It's 1. 1 to 1. Because all the energy is being transferred into this object. It's being converted actually into heat when we said about it. How about a pane of glass, a pane of window glass? Shine a light beam at the window glass. What would that SWR be? It's going to be 1 point something probably, because some of it's going to reflect back. The glass has a reflection characteristic, but most of it goes through. So if you're thinking about SWR, it's reflected energy, and it's very easy to visualize if you think in terms of light. Does that help?
Mm-hmm.
Okay. Why does SWR matter? I will tell you this. The amount of energy that's radiated from your transmitter really does not care about SWR. And the pattern of your radiated signal is not at all influenced by SWR. What is impacted by SWR?
The whole totality.
It's your transmitter. When large amounts of energy are reflected back to the transmitter, the voltage on the output devices increases. Most transmitters are designed to handle a maximum SWR of 2 to 1. And so here's an example of what happens. If you have an SWR of 2 to 1, the output voltage, now this is a 100-watt transmitter. The output voltage of that transmitter rises 33% to 94 volts. 100 watts, if you do the math, it's 70.7 volts is what's on the output. If the SWR gets to 10 to 1, now you have 223 volts on those output transistors. And if heaven help you, if you got a 25 to 1 SWR, now you have 353 volts on those output transistors, and that's when your transmitter turns to smoke. You let the smoke out. So SWR, from the standpoint of your operation, its main issue is damaging your transmitter. Okay? Makes sense? So we're going to switch gears a minute. We were talking about AC stuff. Light is AC, alternating current. Radio waves are alternating current. Now let's talk about something that everybody's heard of, Ohm's law. And Ohm's law is actually incredibly simple. All that Ohm's law states is that if you apply 1 volt across a 1 ohm resistor, 1 amp of current will flow. That's all that Ohm's law says. And there's a whole bunch of manipulations of that basic premise. You can figure out what the voltage is if you know the current and the resistance. You'll know the resistance if you have the voltage and the current. You can find power by using both the current and the resistance, or the voltage and the resistance. But the bottom line is, all that Ohm's law says is 1 volt of voltage across 1 ohm of resistance will cause 1 amp of current to flow. You're all experts now in Ohm's law. This does matter. We're going to get to something where it really ties it together. Let's talk about another principle here, the principle of resonance. So I'm going to ask you a question. Why is it when a car tire is out of balance and it at a certain speed, it's the most pronounced? You're driving down a road, a wheel weight falls off your car, and you get the shake. But only at 1 speed. It dies down as you go up in speed or lower in speed. Why is that? It's resonant. And what is resonant in that instance?
The same spot on the tire is hitting the ground in exactly the same place as it rotates.
That's true, but what's vibrating? It's the entire car body that is absorbing the most amount of energy at that particular rate. It's natural mechanical resonance is the frequency at which that tire is slapping the ground, just as you described. Let's talk about another example. A washing machine. You know, you got clothes in a spin cycle, and at 1 speed, there's not much going on. And as the speed increases, you get to a certain point where that machine is shaking like crazy, and it goes a little faster, it settles down again. Why is that?
Harmonics.
It's exactly the same thing. The frame of the washing machine has a natural resonance. I don't know if you ever heard of this guy, Nikola Tesla. But Tesla was credited with darn near taking down an entire building in New York City with a little device, a little hammer, that beat on 1 steel beam at a certain frequency. It happened to be the frequency at which that entire building structure was resonant. So that building started absorbing more and more and more energy until the whole thing was shaking. Mechanical resonance. We have an equivalent in the electrical world. And what did I list up here? In the electrical world, there's a thing called a tuned circuit, which is a capacitor and a coil of wire. And what happens is the energy that's in the capacitor will discharge into the coil of wire, and the coil of wire will absorb that energy till it discharges, but there's a certain frequency at which those two match up. It's electrical resonance. Another resonance, a swing. You put a child in a swing, you'll find that no matter what you do, no matter how fast that child goes, the swing goes at exactly the same rate. It may go higher, it may go lower, but if you count the time from top to top, back and forth, it's always the same because of the length of the swing. The same is true of a pendulum and a clock. So a pendulum clock works. It's this natural motion. So in the electrical world, we talked about the tuned circuit. We're going to play with one tonight. But there's also an electrical resonance for an antenna. And the thing that you need to know about antennas is that remember we talked about that 30 megahertz signal. It's a 10 meter long wave. Well, antennas, the shortest length of wire that will resonate is one that is a half a wavelength long. So that 10 meter signal we were talking about, how long will a piece of wire have to be for it to resonate?
5 meters.
5 meters, exactly right. And if you do the math, we're going to do that in a few minutes, you'll find out that it's exactly how it works out. Half a wavelength antenna is the shortest length of wire. It is resonant. Okay, we've talked about the concept of resonance. We talked about this half wavelength of wire. This is a diagram of a dipole antenna. And they call it a dipole because there's two halves. There's one pole, there's the other pole, and in this case we're feeding it in the middle. By the way, you don't have to feed it in the middle. So this is the dipole antenna. And practically every ham has been around for a while that built the dipole antenna. I mean, the wire, the insulator, use a feed line to your generator. How many here have built the dipole antenna? Pretty much everybody, right? Mm-hmm. And the dipole antenna has some unique qualities. It radiates off the sides of the element. And remember I told you that there's three numbers? Remember 300 million, we talked about that at first. So we got an Ohm's law with the, and we dealt with the number 1, right? Well, here's our final number. The length of a half-wave dipole antenna is approximately 468 divided by the frequency in megahertz. So let's use my example. Let's take a 30 megahertz signal. And I told you that a 30 megahertz signal, a half wavelength of that is 5 meters. 5 meters, by the way, is 16.4 feet. Mm. So who's got a calculator in? You take 468 and divide it by 30. 468 divided by the frequency in megahertz.
468 divided by
30.
30. Okay.
You come up with 15.6.
Show enough?
Show enough. That's pretty damn close to 16 feet and whatever I said it was, 16.4 feet. So the reason for the difference is there's this property of antennas called end effect. But for purposes of estimating what it is, it's pretty darn easy to figure in terms of meters. And a meter is roughly 3 feet. You get pretty darn close, don't you? So you can almost look at an antenna just by looking at it. You know what band of frequency it's typically. Pretty easy, pretty straightforward, and it's pretty darn accurate. Another interesting thing about antennas, if an antenna is exactly a half wavelength above ground, the input impedance is going to be about 72 ohms. So let's see how we get to 72 ohms, shall we? Why do you care about the 72 ohms, by the way?
It's going to be line. Feed line.
Feed line, exactly right. What kind of feed line do you want to put on an antenna that's 72 ohms? You'd like a piece of 72 ohm transmission line, right? And I think that this is the most illustrative portion of this presentation. In the upper drawing, we have our dipole antenna. You like my fancy battery? I did that all by myself. So you have a battery connected between 2 hunks of wire, and we know that 2 hunks of wire split in the middle, we call it dipole antenna, right? So if you take a voltmeter and you measure across the antenna, you're going to get the voltage of the battery, right? No question about it. And if you put an ammeter in this circuit and you try and measure how much current's flowing in that piece of wire, what are you going to get?
0.
Hank said 0. He's exactly right. DC, you're going to get nothing. But watch this. See that? That's a switch. So if you were to take that same battery and that same dipole, and you were to flip that switch 30 million times a second, those are fast fingers, by the way. Guess what happens? If you measure the current flowing from the switch battery, you're going to find it's a real number. The ammeter is going to read some current. Nothing's changed other than you flicking the silly switch. And if you take those numbers, if you divide the battery voltage by the measured current, you're going to get a value of
72
resistance.
ohms.
Or actually, in this case, we call it impedance. How can that be? The only thing that changed is the switch. And it's a property of inductance and capacitance. The very things I say constitute this resonant circuit that we talked about. The guy that discovered this was a fellow by the name of Michael Faraday. Michael Faraday, believe it or not, served his apprenticeship, to get this right, he was a bookbinder. And at the age of 14, he was indentured as a bookbinder. And he got to working for one of the scientific institutes, or they published books for one of the scientific institutes of Great Britain. And he read the books. He fascinated, and he finally got a job doing laboratory assistant work in this institute in Great Britain. He later became one of the foremost scientists of his day. And he compiled an incredible list of information, but he didn't have the skills to delve into the mathematics to define his discoveries. And this fellow, James Clerk Maxwell, found Michael Faraday's work, and he wrote a whole series of equations. They called them Maxwell's equations. Unfortunately, Maxwell's equations were so complex, there were only a handful of people on the entire planet that could decipher and understand them, until this guy, Oliver Heaviside, came around in 1885, simplified the equations down to, I believe it was 6. And that's what we call Maxwell's equations today. But that mathematics defines what's going on when you flick that silly switch. Don't you think that's amazing? It's absolutely unbelievable as far as I'm concerned. So let's talk some more about this antenna radiation resistance, which we call antenna feed point impedance or surge impedance. This is a chart out of the ARRL antenna. And listed in the bottom is horizontal height in wavelengths. So that's 1/10 of a wavelength, 2/10 of a wavelength, 3/10, 4/10, half a wavelength. If we go up here, you'll see that 70 ohms is here. Over those two cross, 72 ohms is the intrinsic impedance of a half-wave dipole, a half wavelength above ground. So for a 30 megahertz signal, how far off the ground would that be? You've already given me this answer once.
10 feet or
It's
5?
5 meters.
It's 5 feet.
Half a wavelength of 10 meters is 5 feet. And if it was a 20 meter signal, a 15 megahertz signal, how high above the ground would 72 ohm feed point be?
10.
10 meters. And that's literally all there is to it. Isn't that simple?
Okay.
So, this is the effect that the Earth has on radiation resistance of your antenna. That same switch flicking thing that goes on. What do we call our switch flicker?
Frequency.
Our transmitter.
Our transmitter. Okay.
Our transmitter is our switch flicker. So, now there's a couple things we can do with this newfound thing that we've got. We've got an antenna. We know it's got this radiation resistance property. We know that if we put a voltage across it, it'll switch the voltage and read the current. And we know that we can translate that into a feed point impedance. And we know that it's impacted by how far it is above the Earth. We're doing pretty good so far, aren't we? But it's damn hard to get the transmitter 10 meters up in the sky and operate it, isn't it? So what we typically do is we put a piece of transmission line from the antenna down to the river. We all do it. We call that transmission line typically coax, but there's all kinds. You know, there's, well, I didn't put them all up here, but there's twin lead, there's open ladder line, there are wave guides that they use in microwave frequencies. They're all transmission lines. You know, in today's world, if you got a real high-speed internet connection, what's the transmission line between the source of the internet signal in your house?
Fiber optics.
Fiber optics. It's a piece of light tube is a transmission line. Same stuff, only different. Here's the other part. What you'll find is that if your antenna is at a different frequency than its half wavelength, right? It's not going to be 72 ohms when it's a half wavelength above the ground. It's going to have a higher impedance or a lower impedance. And what that causes, remember we're talking about this SWR thing? And why do we care about SWR?
Protect that expensive transmitter.
So we buy these antenna matching things, right? This one happens to be an MFJ antenna matching. So what this thing really does is it goes between your transmitter and the feed line that goes to your antenna. And when you adjust these knobs and dials so that the transmitter is happy, it in turn provides what's called a matching network so that the signal goes out on the feed line, the transmitter is happy, and energy goes to the antenna. But what you may not know is that the losses that were in the feed line before, the SWR on that feed line, is exactly the same. It didn't get any better. The SWR on the feed line going to the antenna is exactly the same as when you started. It's just the transmitter doesn't see it. And so you're going to lose some energy in the matching network. You're going to lose some energy in the feed line to your antenna. But you're able to put out a signal without having to put up a new antenna or make a change to the antenna. So matching networks make your rig happy, and so you can get the job done. So let's talk about the dipole again. We talked about this a little bit earlier. This is a model of an antenna. An antenna has a characteristic input impedance. We talked about that. 72 ohms if it's a half wavelength above ground, and it's a half wavelength long, right? But there's also this capacitive and inductive, what they call reactance, that makes the antenna resonant at that frequency. And believe it or not, we have one of these. I want you to see, how long would a 40-meter antenna be?
66 feet.
66 feet, or about 20 meters.
6, 7.
That's my 40-meter antenna. What's here is a small inductor. You can't even see it. There's a little tiny surface mount resistor in here, which I'll guarantee you can't see. And there's a little capacitor in here that I can tune so I can make things go up and down. As soon as we finish the slide thing, we're going to fire up my vector network analyzer, and we're going to look at my 40-meter antenna and see what goes on. So, again, a dipole antenna can be modeled as a series circuit consisting of a capacitor, the C, an inductor, the L, and a resistor, R. The resistor is the value of the radiation resistance we spoke of earlier. That's that 72 ohm thing we're talking about, right? The capacitor inductor provide equal and opposite, what they call reactances at the frequency where the antenna is designed. Reactance is AC resistance. And there's a lot more to reactance than what I showed you in Ohm's law, but for purposes of what we're talking about tonight, this is just perfect. By the way, if you want to go crazy, start dealing with all of the functions that belong to AC circuits. And it's all because of that thing and that. That's what drives everything crazy. The math goes through the roof. Isn't that right? You said.
Yep.
Okay, so far so good? Okay. How many of you seen an SWR curve before? You got a little antenna analyzer? They all look like this. So right here at the bottom, where that number 3 is, I think it is, that is an SWR of 1 to 1. Everybody wants to. This next line is when the SWR is 2 to 1. And typically when you're measuring an antenna, you want to know what the 2 to 1 bandwidth is. I don't think I can read that. In this case, for this antenna, this number is at 7.19 megahertz. This number is 6.54. This is 7.4. So the 2 to 1 SWR of this antenna is about 1.5 megahertz wide, which, by the way, doesn't exist in the real world. That's quite an antenna. But these two numbers are at SWR 2 to 1, and of course this is 1 to 1. So how far they are apart is what's called the bandwidth of your antenna, 2 to 1 SWR bandwidth. Now this is the one that will drive you crazy. You like that chirp? You remember when they first came out with cough drops, Smith and Smith? This is the Smith.
Smith Brothers.
This is a circle that describes what goes on when SWR is 2 to 1. So if you find that your SWR falls anywhere in this part of the circle, the antenna is what's called, it's a little short. It's called capacity reactive. If it's up in this part of the circle, it's a little bit long. It's inductive reactive. And if it's right smack dab on this line, it's perfectly resonant at the frequency, and this is your feed point impedance. Right there's 50 ohms. I can never keep this straight. I can't remember 72 ohms here or here. But the bottom line is, it's perfectly resonant at the frequency that you're using that on. You probably won't be working with these. I just wanted to show you that there's a graphical way of looking at your antenna and seeing if it's too long or too short, and whether the feed point impedance is too high or too low. And all the new antenna analyzers you see today produce these kinds of graphs. So what I've done here is, here's our SWR curve, okay? And if you look here, you see this point 2, see this big red circle, kind of semicircle? You'll find that from point 1, or from this point 1, which is this point is 6 point something megahertz, all the way up to point 2, which is 7.5 megahertz. This is that 2 to 1 circle. So if we start here at 6.5 megahertz, remember I said if it's short, it's down in this part. This is short all the way until it gets to here. And then that's exactly resonant at exactly 50 ohms in this case. And if you go on up, the antenna is actually a little bit long. And it's still within 2 to 1. And this upper limit, which is 7.5 megahertz. So you get to see what the SWR curve is. You can tell what's going on with the feed point impedance. And you can tell whether the antenna is too long or too short. That's what the new antenna analyzers give. Is that right, Giuseppe? These all of them. Okay. So, we've talked about resonance, we've talked about feed point impedance. And by the way, these are all terms that you're going to hear every time you look at buying an antenna, tuning an antenna, or dealing with an antenna. So the purpose again tonight is to introduce these terms. So when they come up, you have some idea what they're talking about. Okay? Here's the other thing, and actually this is the most important part of your antenna. You know, one of the things that antennas do is radiate signals at a certain angle relative to Earth. And that's called the radiation angle. Okay? And in this case, this is 5, 10, 15, 20, 25, 30. About 33 degrees is the takeoff angle on this antenna. The lower this takeoff angle, the better it works for DX, right? The higher this radiation angle is, the better it is for working in close-in stuff, but you're not going to talk to too many people on the other side of the planet, right?
Yeah.
So this is one of those patterns that you're going to see that defines an antenna. And this is that takeoff angle that they talk about. Have you guys seen these graphs before and tried to figure out what they mean? That's what it means. The old landline, you're in trouble. Here's another kind of pattern. This is a directivity pattern. This is for a beam antenna. And what we've done here is we've taken most of the energy and we're sending it out in this direction. And what we did is we stole energy from all the rest of it and focused it in this direction. Have you all heard the term antenna gain? There is no gain. You only have so much. It's sort of like a balloon. It's filled with so much air. There's no more air that's going to go into the balloon. It's already in the balloon. But if you squeeze it one way, it all pops out one direction, right? You squeeze it the other way, it pops out the other way. So this term that they use, gain, there is no magic. You don't suddenly invent more energy. You just focus the energy in a specific direction. And that's what this pattern tells you. And I'll give you all sorts of magic numbers like DBD, DBI, and all the rest of that nonsense. So this is what's really going on. All the energy that would have been over on this side has been added to this side. Some of it's still coming out there. You got a little blip coming out there and a little blip coming out there. Antenna gain simply means you've taken a whole bunch of stuff that would normally go out the other side, and you've come up with a method to make it all go out the other side. And so, that's why they had a whole bunch of elements to antennas and one of the gang antennas and a bunch of stuff. Yes, Dave?
If you had a vertical antenna, your pattern would be hopefully a perfect circle.
Well, you can take two vertical antenna elements, and you can generate exactly these kinds of patterns. Some of them, there are people who have 8 elements of vertical, and they use these special phasing arrays to focus very narrow beams. Real tight. It'd be like that in a very specific direction. But again, it's done with this thing they call phasing. Yes, sir?
So by changing the phase, you can change the angle of the lobe without that antenna having to turn.
Right, because you turned it electrically. You don't have to turn it necessarily physically. There's a lot of ways of doing these things. And a lot of very creative people have come up with this. In fact, I think we've got one sitting in our audience here. What he was telling me. Okay, here's another set of terms that you're going to run across. Decimal. Why do we need decimal? Why can't we say it's 10 times as powerful? 32.6 times as powerful. The answer is we could. But say, for example, you have an antenna where you manipulated the pattern, right? So it has what they call 10 dB a gain. 10 dB a gain means it's 10 times as strong as it was before. The energy directed in one specific direction is 10 times as strong as it was before. But if it's 20 dB, it's 10 times 10. So it's 100 times more. 30 dB. 30 dB is 10 times 10 times 10. It's 1,000 times more. This little device that I have here measures down to minus 90 dB. So that's 10 times 10 times 10 times 10 times 10 times 10. 9 times. That's pretty sensitive. What is that? 10 million or 100 million?
100 million.
I think it's 100 million.
Yeah.
The ratio, the high with the low.
10 to the ninth.
Yeah, it's 9 zeros, so it's 100 million.
100. There you go. So that's why they use decibels, because you can deal with very big numbers in a very simple manner. And you can add dB and you can subtract dB. You don't have to do any multiplication. You add 10 plus 10, it's 100 times. Right? If you put in a 10 dB attenuator, you drop the power level by a factor of. And here's some other kinds of dB readings. There's dBm. dB are always ratios. It's a relationship of one to another. So in the case of dBm, it's the ratio relative to 1,000th of a watt. And that's used often in measuring receiver performance. dBm. dBi is a ratio to what they call an isotropic antenna. Has anybody ever seen an isotropic antenna? There are none. They talk about them all the time, but there are none. It's a fictional device that radiates perfectly equally in all directions. We've never built one. Maybe the sun. The sun probably has a isotropic. dBW, ratio to watts. So if you have a 1 watt transmitter and you put a 10 dB amplifier on it, how much power are you putting out now? 10 watts. Put a 20 dB amplifier on it, what do you got?
100 watts.
You got a 100 watt amplifier.
Okay.
And then, they use this in sound too. Ratio to sound pressure level. So dBs are used in a lot of different instances, a lot of different disciplines, but it's a method of dealing with very large numbers and being able to just add and subtract the numbers without having to do a lot of mathematical manipulation. Let's see if I can get out of here. Perfect. So what I want to do here, let's go back over. Oops. Go back. Okay, so here's what we talked about then. We've all heard about wavelength. Does everybody understand what wavelength means? If you have any questions, raise your hand and I'd be pleased to deal with them. You leaving? Well, you better get there. Or you're going to be in trouble. Principal will get you.
He will.
Reflected energy. We talked about that, didn't we? How do we express reflected energy?
SWR.
Right. We talked about SWR. We talked about Ohm's law. Anybody want to tell me how to express Ohm's law?
1 to 1 to 1.
1 volt of potential flowing through 1 ohm of resistance will produce 1 amp
1 amp.
current. Exactly. That's all there is to it. We talked about resonance. We talked about mechanical resonance in washing machines, automobiles, children's swing, a pendulum and a clock. They're all examples of mechanical resonance. And we talked about electrical resonance. And in the case of antennas, what is the shortest length of wire that will affect resonance.
Half a wavelength.
Exactly. We talked about radiation resistance. You saw the chart. I didn't ask you to remember 72 ohms is the classic input impedance of a half-wave dipole, a half-wave length of a third. But you understand how radiation resistance changes as you change the height of the antenna. One of the reasons you can tune an antenna one place, and if you move it, it's different. One of the reasons. The Earth has a profound effect on antennas. By the way, what else affects antennas?
The sun.
What's that?
The sun.
Well, that actually affects propagation because of the ionosphere, but foliage affects antennas. Other material around an antenna, especially metal, affects antennas. Everything around an antenna affects an antenna. If it rains, the conductivity of the Earth changes, and it changes the characteristics of your antenna. It may not change it much, but it changes it, yes.
So, when we have, and we very often do, have antennas above roofs, then do we start counting that as above the ground, as being a...
Well, here's another interesting topic.
You know, where does the ground
Where is
start?
the ground?
Yeah,
Am I standing on ground?
sort of.
Not electrical ground,
No.
as regards to antennas. Electrical earth, electrical ground could be 5 feet down, or it could be right on the surface. About the only one you can really define is salt water. You know exactly where electrical ground is with salt water, or a battleship. If your antenna's on top of a battleship, you got a pretty good idea where ground is. But as far as raw earth is concerned, it varies.
Moisture content, all that sort of thing.
All of it. So we talked about impedance. We talked about transmission lines and why we use them. We talked about matching and what a matching network really does. It makes you transmitter happy. It doesn't change the SWR on the coax to the antenna. It just makes the transmitter happy. We talked about reactance. You know, if the antenna is too short or too long. We talked about something that this Smith chart thing that I'm showing you tonight, I only show that to you so that you can see that there is a relationship between antenna too long, antenna too short, feed point impedance high, feed point impedance low. It's a graphical tool that allows you to plot and graph that. And it also is a great tool to show you how to match your antenna to your feed, which is a whole other science. The dipole antenna, we talked about it. Everybody understands at this point that a half-wave dipole antenna is a very simple antenna. We know how long it needs to be. What's the number that goes along with a half-wave antenna? 468. I always like to say 2, 4, 6, 8. Then throw out the 2. We talked about patterns and what that means, and what a fallacy this word gain is. Gain is hocus pocus. It's just we focused it more, and let's focus over here, right? Hocus pocus. And we talked about the decibel, the fact that it's a mathematical tool that allows us to deal with very large numbers in a very simple manner. We talked about the 3 important numbers that you really need to understand. Ohm's law all revolves around that number 1, right? 468, we talked about that, the half wavelength. You take 468 and you divide the frequency in megahertz into 468, it gives you the approximate length of a half wave antenna for that frequency. It'll vary a little. Why will it vary?
Ground effects.
What's that?
Ground effects being what?
Absolutely. Ground's a very big piece of it. Adjacent objects. The end effect. All that stuff has an impact. How much sag there is. There's all kinds of things that have an impact on it, but it's pretty darn close. If you cut an antenna to a specific length using that formula, just a little bit of pruning, you'll have it exactly where you want it. And in most instances, you probably won't have to do much at all. Okay, so we talked about the terms, we talked about the numbers. Questions? Yes?
Most modern rigs have some sort of SWR meter. I noticed, though, in many ham shacks that people have a separate SWR meter. What advantage does that give you, or why would you want to have it?
I don't think there's any advantage. You know, in a ham radio shack, it's important to have a whole bunch of stuff stacked.
Yeah, that's good.
That's what I thought.
It really looks good.
That's right.
You know, the more stuff, the better.
Yeah.
Like, used to be that way with stereos.
Oh yeah, yeah, and the great big boom boxes. Those are great. But no, if you have an accurate SWR meter, and there's no need to have 6 of them. By the way, they all should read the same. You know who can't tell you what time it is? It's the guy with 6 clocks, right? So if you really want to know what the SWR is, don't have more than one.
If you have the one that's separate, you can use it on more than one radio.
That's absolutely true.
Pay good money for those things.
Yeah, well, I like stacking them up. They look good.
Since 72 ohms seems to be such an important number, why is coax
50 ohms.
and the impedance of almost every ham rig I've ever seen anyway, 50 ohms?
Because somebody decided it should be that way.
World War II.
Say what?
In all fairness, I'm trying to remember where I read this.
I know the military had something to do with it.
Yeah.
Well, most beam antennas, for example, are designed to work into a 50 ohm coaxial cable.
Mm-hmm.
If you deal with UHF collinear arrays, they're designed for a 50 ohm system. By the way, if you go into cable TV stuff, what's that impedance?
45?
75 ohms.
75 ohm, yeah.
But, you know, there's more than one way to skin a cat.
Mm-hmm.
And, you know, you can build what's called an inverted V antenna. And so when you take the dipole antenna and you drop the ends down, it'll get very close to 50 ohms.
Mm-hmm.
Everybody here seen a ground plane antenna? You know what those
Yeah.
are? That's the one little thingy, vertical element, and it's got the spokes coming out underneath it.
Yeah.
Well, those spokes, as you bend them up and down, you change the input impedance of the antenna. You can get it exactly 50 ohms by bending those up and down, because you're changing the relative relationship of the ground plane to the driven element. Yeah.
And now that's your ground plane, not the ground.
Right. So remember we talked about the dipole antenna? Dipole antenna, you got the 2 halves. Well, in a ground plane antenna, the vertical element is a quarter, it's half of the whole thing, so it's a quarter wavelength. The ground plane, these 4 spokes or 3 spokes, constitute the other quarter wave. Quarter and a quarter make a half. It looks this way in a dipole. In a ground plane, it looks this way.
Okay.
And there's also vertical dipoles.
That's what yours
There's
is.
no reason you can't have a vertical dipole. They work quite well, actually. You'll find that if you were to work with nothing but a half-wave dipole antenna, that's a J-ball. It's a ground plane. It's your mobile whip. It's a vertical antenna. What else falls in that category? Collinears. They're all based on a half-wave element. A beam antenna. If you do a quad, they use a full-wave radiating element. A quad antenna. At field day, we had a full-wave horizontal loop. They call it a loop skywire. It's longer than a half wave. I just said that a half wave is the shortest piece of wire you can have. That doesn't mean you can't have a longer piece of wire. Did you also know that there are types of antennas that are non-resonant? An antenna does not have to be resonant to work. Did you know that?
It'll radiate something.
What's that?
It'll radiate something.
They all radiate. Some of them quite well. Have you ever heard of a beverage antenna or a rum antenna? They perform incredibly well. So there's a lot of different kinds of antennas. But again, tonight's purpose was to just present these terms and what they mean, and those three numbers, and how they fit together to give you a good, solid footing on dealing with this issue of antennas. So the question is, did you find this helpful?
Yes.
I just wanted to add something that before we talk about the 2 SWR meter.
Yes.
If they read different, beware, because there is a problem. Add a piece of coax and see what happens.
Would anybody like to venture an opinion as to why?
What was the question?
Have you ever heard the term, what am I trying to say? The
Common mode.
That's exactly right. It's common mode. It's when the antenna feed line is also radiating signal.
Skin effect.
And that's why you hear balance and common mode chokes. Mm-hmm. That's typically the reason why. And there's all kinds of things. I was talking to somebody at Field Day. Oh, I know it was Jason. He said that he lived in an apartment and he used the rain gutters in the apartment as his antenna, and he got it working pretty well. He said then one day he brought home his 600-watt amplifier. He fired that puppy up, and he was pretty happy until he got close to the microphone and he got an RF burn on his lip.
Yeah.
That's another example of feed line radiation.
Came back.
Yeah, great example.
But also because the feed line resonates. So basically, if what happens if you have an electrical health wave of coaxial line, the impedance that you have on one side is exactly the same as the other side. But if you have a shorter distance,
or a quarter wave,
yeah, then it maxed up. That is why it's important when you have when you read the SWR to add a piece of coax and see if you have the same reading on the 2 SWR meter.
I'm going to do one other thing here. Okay. This is my favorite little tool. Okay, this is, the live demo portion of this. And we talked about this ever so briefly. I told you that this graph, this here, is called the Smith chart. No cough drops involved. And that this curve is the SWR curve that every ham radio magazine in the world publishes when they show you how well an antenna works. Is always one of these SWR curves. And again, the important thing about these SWR curves, see, this is 1 to 1, 2 to 1, 3 to 1, 4 to 1, all the way up to 10 to 1. I can change that. I can go in here. Oh, this screen's too early. Let's,
Phil,
yeah.
if you have an SWR reading of 10 to 1, how do you reduce that to maybe 3 to 1 or 2 to 1? Or is there such a thing as doing a reduction?
That's what the matching unit does. Your antenna matching unit, your transmatch. It takes what the antenna is presenting as a load, and through the use of these, what they call reactive components, there's a capacitor and an inductor inside of that box. And by manipulating the values of those, it reduces the SWR to your transmitter. But there's other ways to do it. There's there are what typically are called L matching networks, which is a combination of a capacitor and an inductor that you can do at the antenna. You can change the characteristics of the antenna. Remember I was talking about the ground plane and how you can bend those radiators, the reflector elements of the ground plane, and that'll get you closer to match. You can put what's called a gamma match on the element, which is, there's a whole series of different types of matches. There are what are called coaxial stubs, which are pieces of coax that you can use to perform this match. There's no shortage of ways to perform a match. Yes, Paul?
But all of the matching devices are at the expense of power output, right?
No.
No?
No. The most efficient method of getting all the power possible to your antenna is to use a feed line that matches your transmitter output impedance, and at the antenna, do the matching. At the antenna. That way you don't have these feed line losses. Some of the energy used to perform the match is absorbed by those elements doing the match. It could be a coaxial stub, it could be an LC network, it could be a gamma match, what they call a gamma match, there's a beta match. Wasn't there a Betamax TV thing?
Yes.
So there's all kinds of ways. But again, for most practical purposes, most of the guys just use this transmatch to get it done. But you do lose some energy in the process. Did that cover it? Okay, so let's talk about this. So now I've changed this thing so that each of these grids is 2 to 1. Or each is 2. They were 10. Oh. Good. 2. 7.21 is 1.11. Well, let's play with this. So I've got this little capacitor. And this is this antenna way up in the sky, right? We're half wavelength above Earth. And so as I change, let's get in continuous. When this thing squeezing all the time.
No sync. Call plumber. No sync found.
But what we'll be able to do, we'll be able to change the resonant frequency of the antenna by changing that ratio of capacitance to inductance. The way you do that in a dipole antenna is you make it longer or you make it shorter. That's all you do. It does exactly the same thing that I'm going to demonstrate here.
Can you make it shorter by folding the end? You know, like we typically put...
Folding it back on itself? Sure.
Yeah. So you can tune it by...
You know, one of my favorite tricks with dipole antennas was actually cut them a little bit short, and then I solder a lead on the end of it to drop straight down. And then I could just snip off a little bit of it and save me having to rewrap them every time as, you know, you try to shorten it and stuff. And then you find out you cut it too short. It works pretty well. Make them a little shorter and put the tail on it. Okay, so we've got this all put back together. Let's see if we can work again. And let's stop this. Let's close this. There we go. Okay. We have no antenna hooked to it, so let's put the antenna back on. So this thing's scanning now.
And it's actually seeing you touch
So you see where the curve is? It's kind of bouncing around a little bit.
Mm-hmm.
Yeah, and it went all wonky while you were touching it, too.
So let's put that finger in here. So I've changed. See how the resonant point went lower in frequency? See, this is lower than frequency, this is higher in frequency. So right now the resonant point is right there. And let's tag that.
And the resonant point is not getting a 1-to-1 ratio.
Well, let's see what it says it is. Here's a new marker. See where that number 4 is there? Number 4, right here. And it's telling us that point is at 6.91 megahertz, and the SWR is 1.02 to 1. Is your antenna that good? That's pretty good, right? So that's the resonant point. But again, as I change this, see, it shifted some more. And now it's at 6.79 megahertz, and it's lower in frequency. And it's still lower in frequency, still lower in frequency, still lower in frequency. And then, remember that Smith chart thing I was talking about? You see where these positions are on the curve? We're now at 3.78 to 1, it's 6.91, which was this 4. This is a 2-to-1 circle. The only thing close to the 2-to-1 circle is this point, which is number 1. Oh no, this point. We don't have it. Let's put that in, shall we? We're going to put a marker right here. Now the resonant frequency is 6.29, right here, and that's 1.04 to 1.
And then on the Smith chart, is the 5 right there in the center?
The 5 dead spot on.
2-to-1 circle.
Yeah, it's in the middle of the 2-to-1 circle.
Yeah.
So this is a perfect match right there. And we're awful darn close, aren't we? 1.04. This is a lot easier than trying to get up on top of that antenna. Yes?
When you said you're fiddling with something, what are you turning?
Come here, I'll show you. The miracles of modern treachery.
You're tuning the coil, not the capacitor, right?
I'm tuning the capacitor. You see this little thing here? That's a variable capacitor. And this is a coil. Remember I showed you this coil? And over here there's a little tiny resistor. Those are the 3 elements that make up the characteristics of an antenna. We're modeling this. We're pretending that it's an antenna. And on the screen, it looks exactly like a real antenna would. I don't think anybody disputed there's that SWR curve. And again, I showed you how the Smith chart tells you whether the antenna is too long or too short for the frequency you're interested in. So this isn't what normal people do.
The device.
What does that make you feel?
That's really just test equipment to test your test equipment.
Well, it's a model of an antenna.
Yeah, okay.
In this day and age, so much design work is done by building mathematical models of whatever it is you're trying to simulate. Well, this is a physical model of what we're simulating.
It's not actually going to transmit or receive.
It'd be a pretty lousy antenna for those purposes. So let's change this back a little bit. Let's move the curve back the other way. And this is exactly what happens, by the way, when you go to tune your antenna. Now we're pretty darn close to dead center as far as frequency is concerned. Did I hit another marker in here?
Yeah.
Sometimes you run out of markers. Oh, okay. So right now, my antenna, I moved its resonant point to 7.5 megahertz. That's right here, which is position number 6. Position number 6, you see how close that is? The dead center. It's not, up here it's too long, down here it's too short. So it's right on the line, right on that line. And at this point on the line, it's exactly 50 ohms. So this antenna is 50 ohms, it's not too long, it's not too short, at 7.5 megahertz. Mm-hmm. But let me clear all these markers, because it's getting really cluttered. Let's put this one back. Okay. So there's our 7.49, pretty close. 1.04 to 1. So let's see what's going on at a different frequency. Yeah, like this. Okay, let's see this is 7.5. This is 5 megahertz. This is 10 megahertz. So 6, 7, 8, no, this is a half a megahertz. So this is 5.5, 6, 6.5, 7, 7.5. So let's go down to 6.5 megahertz and see what the SWR is to 6.5 megahertz. SWR 12 to 1. That works with it. Well, it'll work, but your transmitter's most unhappy, right? So let's see what this thing does for us. I think this is the weirdest gadget mankind ever came up with. So now, I got a little off, 6.93 megahertz. Yeah, I've got two. This is 2 to 1, 4 to 1, 6 to 1, 8 to 1. I really screwed this up. I changed this. Should have stayed at 1. But you can see as you change frequency where this is. And then on the Smith chart, point number 3 is clear down here, which means the antenna is way too short for the frequency. As you go lower in frequency, the antenna needs to be longer. As you go higher in frequency, the antenna needs to be shorter. And it demonstrates that vividly. So this is a graphical representation of what happens to your SWR curve as you make the antenna shorter or longer. And I'm making it shorter or longer by manipulating a capacitor. But in real life, exactly the same thing would happen. If you took your antenna, you had it hanging 66 feet in the air, by the way, at half wavelength, 40 meters. And you went up there and you cut a foot off your antenna on either side, and you were to measure it, you'd find that the frequency went up, but the resonant point went up, but the feed point impedance is going to stay pretty much the same at that new resonance point. At the old resonance point, that feed point impedance jumps all over the place. And it's just a graphical, visual representation of what happens as you tune an antenna.
You're varying capacitance to change that now?
Yeah, but that's my model.
Yeah.
In the real world, you use your dikes. Right? You use your dikes and you make the antenna shorter. You don't use your dikes to make it longer.
Yeah.
You start splicing.
You use a stretcher.
Yeah.
You need a stretcher. That's exactly right. Any questions about my magic gadget? By the way, this thing goes all the way up to 1.3 gigahertz.
Wow.
You know these guys that have 2-meter repeaters and they have the cavity resonators and all that stuff? This thing will allow you to tune those cavity resonators like a snap.
You built that thing, right?
Well, it was a kit. It was a kit. Actually, there's 2 printed circuit boards in there. I've had this now for about 10 years. In fact, I bought another one, the latest version of it, because I wanted to. But again,
so he can stack them up.
There's a lot of these devices in the marketplace. This is not what you call an antenna analyzer. This is actually a vector network analyzer. And they call it vector because it measures phase, which is something we really didn't get into tonight, and it's a whole other world. But there's a number. You've got an AIM 41.7, which is a network analyzer that's been around a long time. MFJ has got some network analyzers. There's one called an N2PK. I built one of those as well.
Step-by-yard has one also.
I'm sorry?
Step-by-yard.
Step-by-yard's got one, yeah. The N2PK has a dynamic range. Are you ready for this? 140 dB dynamic range.
Wow.
Which is just right on the edge of how good a Hewlett-Packard or an Anritsu or any many of those guys are. 140 deep, which, again, we saw how those numbers range. That's 1 to 10 to the minus 14. So, pretty impressive stuff. All this stuff is available in the hand radio world. So if you want to build an antenna for 1.2 gigahertz, you can measure that thing down to a gnat's patootie with the devices that are available today. It's rocket science in your backyard. Put a man on the moon.
It's relatively inexpensive too.
They are. This one, with what they call a calibration kit, and with all of these you need to calibrate them because, again, the accuracy is so tight. Every time you add a piece of feed line, it changes your measurement. And so with one of these, you can actually take your feed line. It goes to your antenna. At the end of the feed line, you can perform this calibration. There's an open connection, a dead short connection, and a 50 ohm connection. The computer measures what goes on at the end of the piece of the feed line, which allows you to measure the antenna at the antenna itself. A coaxial transmission line is actually an impedance transformer. If the antenna is 50 ohms and you run a piece of feed line to it, and it's a 50 ohm feed line, it'll measure exactly what the antenna is. But if the antenna is 96 ohms and it's either too long or too short, and you put a piece of feed line on it, the measurement you get at the end of the feed line is not what's at the antenna. The feed line changes the numbers. And that's why you can use coax in these forms they call stubs to match your antenna. They act like capacitors, or they act like inductors. They transform the impedance, which is a whole other